Hello, my name is Denis, and I'm happy to present our work, which is about key recovery attacks on approximate homomorphic encryption schemes. And this is a joint work with Qian, Elias, and Thomas. What we did, our main contribution, is we showed that in the event when we have a non-worst case noise estimation for approximate homomorphic computation, we can actually recover a secret key. And this works even for passive adversary. And we showed the example of such attack against a popular library called OpenFHE. Let's start with some preliminaries, specifically homomorphic encryption. You can treat it as a public encryption scheme where we are allowed to do some special operations over ciphertexts. Specifically, as an example, if we take a function which is addition, we can encrypt two plain texts, M1 and M2, and do special operation evaluation. And when we decrypt such a ciphertext, we get an M prime, and M prime is equal to addition of the plain texts. So we can do sort of operations over ciphertexts that translate to operations over plain texts. And it works for other functions such as multiplication or combinations, etc. And approximate homomorphic encryption scheme is similar, but instead of equal sign, we get an approximate sign. So M prime deviates slightly from the expected result. And there is a scheme called CKKS. It's the most used, the most popular approximate homomorphic encryption scheme. And it works over lattices. So first we take a ring LW sample, AS plus E, where S is the secret key. We add the message M, we get a B, and so our ciphertext is just a pair AB. And if you want to decrypt such a ciphertext, we subtract from B A times S. As a result, we get M plus E, which is approximate output. So it means that we get a message M, which with a small noise E. And with such a scheme, there is an interesting attack that was pinpointed in EUROCRYPT 21 paper. In the case when we announce decryption results. So imagine that the adversary sees the ciphertext C, and it sees the decryption result M plus C. Then he can compute A times S, which means that there is a leak of secret key S. So like if the A is invertible, we can directly recover S. If it's not invertible, then we need to have a few such pairs, ciphertext and the result. But in any way, the passive adversary can recover secret key quite easily. And in order to combat this problem, the same paper, they introduced a new security model called INCPAD, which is adaptation of regular INCPA to the approximate homomorphic encryption case. And in this model, what happens is the adversary can choose the input M and the function to be evaluated, and the adversary sees all the ciphertexts that are produced and the final result. And the authors show that in order for this scheme to be secure, we need to modify the decryption function slightly. So it's exactly as before, but we just add a new noise in U, and this is sometimes called noise flooding. And what happens here if we try to do the same as before? Instead of just A times S, we get A times S minus E in U, which is a new ring LW sample. And if this noise is big enough, then the secret is still unknown. But there is an interesting thing that during homomorphic operations, there is a noise that grows during these operations inside the ciphertext. And the added noise in U have to grow with it. Otherwise, if it's not the case, or if this noise grows slower, then we show that we can do key recovery. And well, if we can do key recovery, then the INCP is also does not hold. And with a few simple mathematical operations, the adversary can, by choosing specific inputs and the function to be evaluated, he can get a ring LW sample with a E attack, where this noise E attack, it essentially gets as smaller as grows the ratio between the noise of the ciphertext and the noise of the added noise in U. So, which means that if the ratio gets bigger, it's better for attacker. But here's a problem that in the real world, large E in U hurts the performance. Therefore, the libraries that implement schemes, they don't really want to use large added noise. So they use one of the two approaches. First one is the empirical noise estimation, where the owner of the secret key tries to estimate the expected noise that the real computation will produce. But this kind of contradicts INCP model, since it kind of assumes that the adversary will use the same function as the one during the estimation, which is not true in general. Another thing that it makes added noise to be a constant, essentially, and the constant, it does not grow. And there is a second approach, average case estimation. And here it's the dynamic, and in each ciphertext there is a bounds on the noise, and during the homomorphic operations, the various heuristics are used to compute new bound. And what is interesting there is essentially assumption that the ciphertexts are independent, which means that if we add two independent ciphertexts, the noise bound should be square root of 2 times larger. Whereas if we add the same ciphertext, we can get the noise 2 times larger. And this idea, essentially, what we do in our real attack, we abuse the expectation versus the reality. And this both approaches, they can lead to key recovery attack when we use a big enough function f and some special inputs. And in our paper, we claim that instead, the worst case noise estimation should be used to prevent such an attack. And we did attack on the OpenFHE. And in our attack, we consider average case estimation, while the OpenFHE actually uses empirical noise estimation. We do that because average case estimation is harder to attack, and we wanted to show that even if in this unfortunate scenario, the attack is still possible. So what we do in our attack, we consider a simple function, GT, which just adds together T ciphertexts. But the adversary, he computes GT, where as an input we submit the same ciphertext T times. And what does it mean? That instead of the noise that we expected to be square root of T times the original noise, we get T times the original noise. So there is a huge discrepancy between them, which means that if we increase T, as we can see in the figure, the noise gets smaller, and the figure shows the weight of the added noise. So if the weight is 0, then there is no noise. And we can see that the value of t to the 2 to the 57, the noise is just constant 0, which means we don't have a noise, and we can trivially recover a secret key. And here it's a small interesting note that the adversary can actually compute this GT quite fast by doubling the ciphertext log t times. And doing so, we show that there is a possible to recover the secret key in just about a minute on the moderate side computer. And thank you for your attention.